Before we start our first digital lesson, I'm going to go over the notebook and just sort of review how your notebook is already set up, and then also go over some of the specifics of what you're going to see in today's lesson. So inside your front cover, you should have this yellow cast reference sheet. This is the reference sheet you get to use in all of your assessments in my class. Today we're going to be using and learning and talking about this equation right here. W equals m times g. Remember, the variables are listed over here. M is for mass, the lowercase w is for weight, and little g is for acceleration due to gravity. At the bottom of the page you have your constants, and acceleration due to gravity we'll find out is equal to 9.8 meters per second squared, and this is the value for acceleration due to gravity on Earth. So we'll be talking about this today. Then over here you have your table of contents. Okay, this is for second semester, we've already gone through Unit 5. We finished the assessment on the summative on Unit 5. So today we're going to be starting Unit 6, Forces at a Distance. And today's learning target is going to be 6.1. Use a mathematical formula to predict the gravitational attraction between two objects, etc. And we are going to jump over to page 40 to make sure we're all starting on the same page 40. So this is our table of contents, and as the weeks go on, we'll be moving down on these topics. Then over here on the right, remember, this is your variable list. The variable, their units, their name, and the page that your variable's on. We already have these variables down for the semester. Today we're going to be talking about, there's our W for the weight, which is also called force of gravity. It's going to be measured in newtons, and it's going to be on page 41 where we put this in our notes. So you should already have all these pages in here from earlier in this semester. We are going to be jumping today, just to be consistent, we're all going to be going over to page 40. So you'll see this later, where we have you write down learning target 6.1 and copy all of this down for learning target. We will come back to this page on another day and put in some examples of how to answer or how to complete this learning target on your assessment. And then today we're also going to move to the next page, page 41. You're going to be gluing in this note strip. A couple things first. I want to let you know, remind you, the notes, this is Unit 6, Note Strip 1. So that's how you can keep track and make sure you're gluing in the correct note strip at the correct time. And here's the title of the note strip. When you guys glue in the note strips, again, make sure you glue them down past the red line, pretty much as far over to the left as you can get them with a little space. And we glued them on the top like this because you need all this area over here to write your notes. As you're writing your notes, try to keep the notes lined up correctly with the actual printed notes. At any time, if you run out of room over here because maybe your writing's too big or you mess up, you can always go over here and add the notes for this over to this side over here and add notes on this side of the page, on this blank page, so that way you have all of your notes that you need to go with the note strip. And then you should also have, behind it, the other pages numbered so that we can continue our work throughout the next few weeks. Although after today, after today's page 41, you guys are going to end up, depending on how big you write, things like that, your pages will not likely match exactly what my page numbers will look like later on as we go through the next couple weeks. All right, so let's get started. So today, day one, our objective, you guys are going to learn how to calculate the weight of an object in different locations in space. So here's our table of contents. We finished Unit 5. We are now starting Unit 6, Forces at a Distance, and today's learning objectives right here, learning target 6.1 is the learning target we're starting today. So you're going to copy this learning target on page 40, just so we can all start on the same page and start consistent. We all turn to page 40 and copy this learning target from here onto the top of your page, page 40, learning target 6.1.
Use the mathematical formula to predict the gravitational attraction between two objects in relation to product of the masses and distance between. Here's our equation. It's f of g equals capital G m1 m2 all over d lowercase d squared. So go ahead and pause the video and copy this onto page 40 just like this, and then write the page 40 on your table of contents. Alright, and next you're going to turn the page to page 41, and you're going to get out note strip Unit 6 1, the first note strip for Unit 6, and you're going to glue it down on the far left side of the page right across the pink line. And when you're done gluing it down, it should be to the far left side so you can write the notes on the right side. So I'm going to go ahead and pause the video here so you can glue in the note strip on page 41. Now you should be set up for today. Here's what we're going to be doing today. Your notes are going to be on the right hand side. Try to write neatly and keep the spacing matching so that it stays with the printed notes, so that your writing stays with the correct part of the printed notes. You can see, for example, we have these lines across here, go all the way across your binder paper from here across there to keep the equation in here where it says weight. So at any time, if you run out of room on the right because maybe you're writing too big, you can always go ahead on the left side, the left page over here, and write some of this over here on the left page. But it's important that you keep these notes with these notes, and these notes with those, and these notes with these, because these, like these letters A, B, C, D, they go with the letters here A, B, C, D on the pictures. So as we go through, try to keep them lined up. Alright, so here we go. Unit 6.1. What is the little g in gravity? So let's talk about free fall. Free fall is the motion of a body when only the force of gravity is acting on it. So go ahead and write in the word gravity right there. Free fall is the motion of a body when only the force of gravity, only one force, the force of gravity. After you write that in there, I want you to read through this and look at it, and let's see if you understand. I'm going to show you 4 free body diagrams. I want you to figure out which of these 4 diagrams matches the description of free fall. So here are 4 different free body diagrams of an object. Object A, B, C, and D. Which of these 4 objects looks like it's an object in free fall? So read your definition of free fall and go through these 4 and figure out which of these 4, A, B, C, or D, mark down the one that you think looks like the best example of an object in free fall. Okay, so the answer was B, because free fall has only one force, the force of gravity. And this is a force of gravity. Gravity always pulls down, and there's one force, force of gravity. This would not be correct because gravity would be pulling up, and that never happens. And then these guys down here are not correct because they have more than the force of gravity on them. This has force of gravity and the force of air. Technically, free fall is when there's no force of air pushing up on, or maybe if there is a force of air, it's a really, really, really tiny, small amount of air, so you can neglect it. So free fall. Go ahead and add this picture, this free body diagram, next to the definition of free fall. There's the box, there's the arrow down, force of gravity, F of G, and there's no air resistance. So I want to show you an example of an object that's in free fall. Here is a ball being tossed up in the air. You can watch, here we go. Now this is in slow motion, so notice how when you toss the ball up in the air, it goes up and it falls back down. It's moving under the motion of gravity. Now, technically, there's air in the room, so air will be affecting the ball, but because of the shape of the ball and the weight of the ball, the air affects it very small amount. So this is the motion of an object in free fall, because it goes up, it slows down, stops at the top, and then it speeds up on the way down. Now, why is this in free fall? Basically, here's our ball. and we draw the free body diagram, it looks like that, force of gravity. If you were going to draw the force of air on there, it would be a very tiny, just a small amount of air like this, force of air up, and it hardly affects the motion of the ball. That's what we mean by an object in free fall. So an interesting thing for objects in free fall, if you look over here, all these objects, all objects in free fall, if only gravity is acting on it, then they're all going to fall, at least on Earth, at the surface of the Earth, they're going to fall with the same acceleration of 9.8 meters per second squared. That's the acceleration on Earth. Everything's going to fall the same. So technically, if you have these three objects all in free fall, for example, an elephant, a cup of coffee, and a feather, if you drop all three of these, or you toss them all up in the air, all three of these will fall the same way as that ball that I showed you in the video. The elephant will go up, stop, and come back down. The cup of coffee will go up, stop, and come down. The feather will go up, stop, and come down. As long as they're in free fall, that's the tricky thing. As long as they're in free fall. What does this mean? So over here on your right, let's write these notes. As long as there is no something, a feather falls at the same rate as an elephant on Earth. What? Now, you probably realize if you toss a feather up in the air in the classroom or at home, something happens to the feather. It doesn't actually fall in free fall because something is affecting the feather. What is affecting the feather in real life that makes it not usually in free fall in the classroom? Goes in this blank right here. As long as there's no something, a feather falls at the same rate as an elephant. Yeah, it's air resistance. That's the thing. Air resistance really affects a feather compared to an elephant or a cup of coffee. Air resistance hardly affects a ball, an elephant or a cup of coffee because they have so much mass, so much weight that counteracts the force of air. But the feather hardly has any weight, so any air on the feather is going to have an effect on it. So it's technically a feather, so a feather drop in a classroom is not in free fall. But maybe if we drop the feather in space where there's no air, then it would be in free fall. So go ahead and fill that in. Why does this happen? So the thing about this elephant and cup of coffee is that they have more weight, more mass. They have more mass than the feather. All right? But when you have more mass, you also have more force of gravity or more weight. They both go up together. So when you have this ratio for the acceleration, force over mass, since they both go up, the fraction, the ratio stays the same. The ratio stays the same, so the acceleration of gravity stays constant. That's how we get this 9.8. Okay? Acceleration stays 9.8 for everything on Earth because the more weight, the more mass, and this ratio stays 9.8 on Earth. So you get constant acceleration as long as it's in free fall, as long as we can ignore the air resistance. So go ahead and draw a line across your notes right here. And the next thing we're going to talk about is weight. So we're going to see if you can sort of come up with the equation for weight, because it's very similar to another very important equation we learned back earlier in the semester. But let's just look at the units for now. So we have weight is W, acceleration of gravity is little g, and mass is m. Those are the variables we're going to use, but here are the units. There's kilograms, meters per second squared, and newtons. I want you to think about where each of these three units goes. 1, 2, or 3. Where does kilograms go, meters per second squared go, and newtons? Line these up. Match these three units with these three different variables. So we will start with mass. Let's try mass. Which of these three, kilograms, meters per second squared, or newtons, is how we measure mass? Mass is measured in kilograms. So I'm going to move the kilograms right there. Mass is measured in kilograms. Okay, Now what about acceleration of gravity? Acceleration, meters per second squared or newtons? Which of these two we use for acceleration of gravity? Acceleration is always measured in meters per second squared. Okay, and now we have one left, weight. How do we measure weight? Obviously, we're going to measure it in newtons. And before I move on, I want you to notice this. See the difference? There's a big difference between weight and mass. Weight is in newtons, okay, and mass is in kilograms. So see, we already know from right here, weight and mass are different. Mass is how much stuff something's made out of, but weight is a force. It's the force of gravity. So it's measured in newtons, okay? So these are the units. Now, what I want to do is we want to go to this equation. You should recognize this equation. F equals ma. This is Newton's second law of motion. Force equals mass times acceleration. So here's our units. Here's our variables. Now what I want you to do is take these three variables and place them into these three variables. And you will see these are the same units that we're using for these variables. Replace F, M, and A with these three variables. Where do these three each go? Okay, let's start with M. Which of these three variables goes with the M? Well, obviously, it's the mass, right? Mass goes right there because it's still mass, kilograms. All right, now what about, well, there's force and acceleration. So we look at these two and figure out where they go. Let's do acceleration. Which of these two is the acceleration? Well, it's acceleration of gravity, G. And now, finally, the force is going to be W. So this equation, if you notice, the force is the weight equals the mass times acceleration, little g. W equals mg. It just comes from Newton's second law. So when we go to our formula sheet, you'll find it right here. W equals mg. And you'll see acceleration due to gravity is 9.8 meters per second squared. So this is the formula sheet. On the formula sheet, you get to use it on all our quizzes. Let's put this in our notes. So here you have on our notes, let me zoom in on this so it's easier to read. What I want you to do is you should have two lines across like this and then copy in, here's our equation. W equals mg with a box around it and then label. W is weight in newtons, m is mass in kilograms, and little g is acceleration due to gravity. So go ahead and copy this down right here. Once you're done copying down, what goes in this box? Acceleration due to gravity, what number goes in here? Right, it's 9.8 meters per second squared. We've already talked about that right here. It's also on our notes right here on the yellow formula sheet. So 9.8 meters per second squared. All right, so we're talking about weight, W. So let's go to our table of contents, our list of variables, and put in there. We actually can use two different letters for weight. We can use W or we can use F of G. F of G is like force of gravity. Both of these can be used for weight. And the units are newtons, that's weight, and we're on page 41. So go ahead and write this on your list of variables on your table of contents. All right, so now we're finally getting to our objective. What do you think happens to acceleration of gravity in different places in space? So what I have here is little guys. I call them little big dudes because they're giant. This is the Earth, and that's like a giant standing on the Earth, but it's tiny on our picture. We have one guy here, number one, he's standing on Earth. We got number two, he's standing on the moon, okay? Number three, he's just floating out in the middle of space, empty space right there. Number four is standing on Jupiter. And number five, this guy here is standing, oh my gosh, he's standing on the surface of the sun. All right, I know he's going to burn up, but still, let's assume these are all the same the same guy standing on in all these different places. 1, 2, 3, 4, 5. What I want you to do is look at this list. These are lists of actual accelerations due to gravity in all these different locations. So I want you to use sort of your process of elimination, some logic. Where do you think each of these numbers will go? Where do each of these accelerations of gravity go in our picture? For example, like what do you think the acceleration of gravity is going to be for this guy out in the middle of nowhere? What about for this guy staying on Earth? What about for this guy on the moon? The guy on the sun? What would their accelerations of gravity be in these different locations? So think about that for a little bit. And all right, let's start with acceleration of this guy right here on Earth. Okay, number 1. Which of these 5 shows the acceleration of someone standing on Earth? Well, we should know this one because it is the 9.8 meters per second squared that we've been talking about today. A little g is 9.8 meters per second squared, so we know the acceleration on Earth. What about the acceleration at 3, right here? This guy standing in the middle of nowhere, okay, or floating in the middle of nowhere, actually. What acceleration do you think he's going to have because of gravity? Which of these do you think he's going to have? Well, it makes sense that he would have no acceleration of gravity because there's no objects nearby pulling on him, so there's no force of gravity on him. He's going to be floating weightless in the middle of nowhere. All right, so now there's 3 left. Okay, 2, 4, and 5. So there's 3 of these left. So now you have to kind of just use your judgment. Now I got 9.8 on Earth, 0 in the middle of nowhere. Where on here do you think will be 270? Where do you think will be 1.6 meters per second squared? And where do you think will be 26.7 meters per second squared? All right, so using some logic, you should be able to figure out, okay, well, the most gravity would probably be right here on the sun. The sun, this guy's being pulled down by the biggest object, so he'd probably have the biggest acceleration. And then we have the smallest. This guy on the moon would have even smaller acceleration than the Earth, okay, at 1.6. And then Jupiter would have, it's a pretty big planet. It's got more acceleration than the Earth, but less than the sun. So here is all of the accelerations of all the objects, of all the guys in different places. So we're going to finish up with talking about their weights. Assuming these are all the same people, astronauts, whatever, standing on these different places, what is the weight of the guy standing on the Earth versus the weight of the guy on the moon versus the weight of the guy standing in nowhere versus the weight of the guy on Jupiter? So we're going to finish up our notes talking about the weights of these different locations. In our notes we have these 4 locations. Oh, I actually have Mars on this one. So let's go in order. A. So just write this down in your notes. The weight of a 60 kilogram man on Earth. Okay. So we're going to be, all these guys are going to be 60 kilograms when we go through it. And we're going to calculate the weight. So we know the equation. The weight is m times g. My question is, what goes here if we plug in the numbers for m and g, and then the answer we get on our calculator once we multiply, what do we get for our answer? All right, we should get 60 is the m, and little g is 9.8, so 60 times 9.8 equals 588 newtons. So the weight of this guy here on Earth will be 588 newtons. Now let's talk about the weight of the same guy in empty space. He's right here floating empty space. All right, and what do you think his weight will be in empty space? Choose the correct answer. It should be 0 newtons. That looks like on, but it's really 0 newtons. His weight's 0 because he's weightless. Out in the middle of nowhere, there's nothing pulling on him. So he's going to be weightless. All right, so now let's figure out the weight of the same guy on the moon. Now the gravity on the moon is 1/6 of the gravity on Earth. So 588 newtons divided by 6 is 98 newtons. So his weight will be 98 newtons on the moon, 1/6 of Earth. And then finally on Mars, the weight of the same man on Mars. What do you think he's going to weigh on Mars? So looking at his weight on Earth, his weight in empty space, his weight in the moon, on the moon, what do you think would be a good guess for his weight on Mars? Just look at Mars versus Earth versus the moon. His weight on Mars would actually be 220 newtons, because Mars is a little bit smaller than Earth, but not as small as the moon. So it's his weight. His weight is going to be less on Mars than on Earth, but not as low as on the moon. So there you go. Go and finish up. Make sure you have all that in your notes, and that is it for today.